Perhaps one of the important questions we should address is exactly what do we need to understand galaxies? And we'll see there are some key ingredients that we need in order to produce and understand an evolution of a galaxy, essentially over billions of years. On the right, you can see the product of a simulation of a galaxy, pretty much like the Milky Way when we run it in supercomputers. We'll come back to that in section 15, but before we can interpret these simulations, it's really important to have a look at some of the ingredients that we need. If you reach section 13, I hope that you actually went through all the other sections and you got at least a basic understanding of, for example, black bodies, and also the fact that when we look at the universe at different wavelengths, we're actually seeing different physical processes and also different temperatures. And this will be crucial to actually interpret what we see in galaxies. On the pictures here, you can see the same galaxy. This is M81, seen all the way from the X-rays to the ultraviolet, then visible, near infrared, mid-infrared, far infrared, and also going all the way into the radio. And what we can actually see is that the features that are revealed by different wavelengths show very different structures. For example, in the X-ray, mostly the thing that shines brightest is in the center. This is because there is a supermassive black hole. But as we move into the ultraviolet, the supermassive black hole is still bright, but then we start seeing the spiral arms. These are essentially being lighted up by O and B stars that radiate very strongly in the UV. But if we move to longer wavelengths, then essentially we're looking at stars pretty much like the sun or even lower mass that are mostly concentrated in the center, but that in the UV, they're basically gone. So what do we need to actually understand a galaxy? You'll see all the details, as always, in the lecture notes, but it's good to go through at least a basic list of the ingredients you would need to actually understand a galaxy and decompose it in its multiple components. In order to interpret galaxies, understanding stellar light is actually really crucial. A galaxy will be essentially a combination of all the stars in the galaxy, but the important thing to understand, and if you go back to sections 8 and 9, that becomes even clearer why that is the case. The galaxy will always be dominated by spectral classes which are the hottest. That is because the luminosity goes as m to the power of 4, or the luminosity goes as temperature to the power of 4. The most massive and hottest stars are actually so luminous that they very easily outshine the coldest spectral types. In addition, we need to take into account stellar evolution. We've seen in section 9 that when stars form in any given location, they will essentially follow the IMF. That means stars which are very massive are rare, and stars that are low mass are very common. But if we let a stellar cluster, for example, evolve, and this will be the case for a galaxy as a whole, if we let the galaxy evolve without forming any more stars, essentially as the hot, massive types die off and leave the main sequence, then the light of something like a galaxy will become dominated by colder and colder spectral types. And therefore, if we take a spectrum of the entire galaxy, we'll be able to see essentially a combination of spectra, but that will be dominated by the hottest or most massive spectral type still in the main sequence. Of course, a galaxy is not just a stellar cluster. It will be a mix of many, many stellar clusters formed at different ages. And what happens is as stars form in the galaxy, the low mass or the cold spectral types will actually accumulate along the history of the galaxy, while the massive hot spectral types do not. They form and they die off, most of them a supernova, but the low mass ones accumulate in a galaxy. Of course, a galaxy, as we've seen, is not just made of stars, so it is really important to understand the galaxy, to understand its gaseous components. There's multiple phases of gas, and typically the gas that's easier to see is ionized gas, and we can see it in, for example, emission lines. Of course, as stars form in these dusty environments must be present in galaxies, and therefore dust is also crucial to study and understand galaxies as a whole. And even though we don't really know what dark matter is really fundamental to understand a galaxy, to predict some of its properties, and also this will be crucial to understand the environment of a galaxy, as we'll see in section 14. And finally, as far as we can tell, every single galaxy contains a supermassive black hole, in its center or core. Some galaxies may even contain two, especially if they're a result of an ongoing merger and the supermassive black holes are still spiraling around until they become one. This supermassive black hole, even though it only occupies a tiny volume in a galaxy, can actually affect it in many ways, as we shall see, especially in section 14.